Hi, I'm William. I'm the Chief Executive of QED, Quantitative Engineering Design. We're a technology company that has been working in international development primarily in sub-Saharan Africa over the past decade or so, since 2012.
Hi, William.
And what we do is...
Sorry, William. Do you want us to share your presentation from our site? We have the presentation. You want to share it from our site?
Yeah, I think there might be some mix-up because originally there's another speaker who's giving that presentation, but he can't make it, so I can give my own presentation if that's okay. I can share it from my site.
Okay.
Okay.
Thank you.
Yeah.
Please go.
A brief introduction about us. What we do is we build technologies to help people collect more data, even in very rugged conditions. So places that may not have stable internet, may not have stable power. And despite all of these challenges, we tried to find a way that we can build digital systems, also analog systems that convert to digital and still get reliable data, especially in the area of agriculture. So yeah, I had to quickly fill in for someone else, so it's a little bit disorganized. I'm sorry about that. But I can share my screen and a few slides of ideas. So please let me know whether you can see this on your side.
Yes, affirmative. Go ahead.
Yep. Thank you very much. Okay, so yeah, as I was saying, we're primarily a software company, mainly 30 software engineers and data scientists, but we also have a few agronomists and epidemiologists. So my background was in computer science, and my co-founders in statistics are agronomist David Lorena, who's in crop and soil science. And yeah, we've been working primarily in East Africa, but also in South Asia and a few other places in the world. So this is a map of some of the places we work in. And so the title of my talk is Practical Technologies for Agriculture. I want to show you some examples of the kinds of tools that we've been building. Load soon. Sure why it's frozen. Let's show it again. I need a black screen. So let me talk about it. Okay, let me do this. I think we can probably see it better if I don't share it in the screen mode. Okay, so for some reason this is not showing up here, but anyways, what we're doing is we build technologies to kind of cross that last mile. So here on the left-hand side, we have an example of where people are submitting photos of plants that may be sick and they don't know what's wrong with the plant. And this enters the phone, then it goes to a web server where an agronomist can then diagnose what's wrong with it. So these are maize plants in Kenya. I think some of the people here in the audience may know this is phosphorus deficiency, for example. So it can also be very useful to cooperate with the fertilizer industry who may want to know exactly what kinds of nutrient deficiencies are out there in the field. And then for a more invasive analysis, let's say you have some problems you cannot just see with a naked eye. Also try to do both dry and wet chemistry. And I'll say more about that later in the talk. We've been involved with certain projects like the Africa Soil Information Service from 2009 to 2019. We're the principal technology partner building the backbone there. And one of the problems I found was the tremendous logistical expense that agricultural players are paying in order to take plant and soil samples from the field and bring them to a lab. And I was also working on these national programs where we have to build entire labs where there weren't any before, erecting solar panels and windmills and things of that nature. So one of our interests is building more sensors where we can essentially take the lab to the field, and do some examples here. And this is the AFSIS project I mentioned earlier, funded by the Gates Foundation. Another thing that we do, let me try to share my screen full again, is to map croplands and houses from the sky. So satellites are very powerful, and we use a lot of imagery from Sentinel satellites as well as Planet and other sources to produce maps like this, where we can see all the houses on the ground and also all the croplands in the area. And so this is another work that we've been doing in heavy collaboration with the Gates Foundation, as well as the BIFA project, to help generate more market information for the fertilizer industry. We know that fertilizer can greatly assist many countries with closing the yield gap, the crop yield gap, but we often hesitate, the fertilizer industry may hesitate to break into certain markets if they don't even know what is the size of the market, like where are all the different crops and how many are there each year. So we tried to produce this kind of up-to-date information for several countries, such as both Nigeria and Ghana. Here on the right-hand side, we have examples of mobile clinics that we're running. So we work in both the agriculture and the health space. And this is an example actually of an HIV clinic. So this truck, which looks like Optimus Prime, is a full hospital, and it's being used to deliver certain kinds of antiretroviral drugs to HIV populations in Tanzania. So here's a map of where HIV patients are based on the traffic coming into the truck, and the truck is driving around and around. But of course, you can do the same kinds of things with agriculture, in theory, if you had a mobile clinic, and I know some fertilizer companies, perhaps in the audience, also have these kinds of clinics, analyzing plants and soils, roving around, and then delivering the drugs that the soil and the plants need. And then here in the center, this is another example of innovation to overcome data scarcity. Again, inspired from the health space, where doctors all throughout Africa are writing information into paper forms. And these paper forms are often not digitized at all. They're not transcribed later. And it's actually not very practical to try to install fully digital systems in all those clinics, because it would be so expensive, and you don't have the power, you don't have the internet, you don't even have running water. So what we do is we built a system where you can continue recording data on paper, and then you just take a photo of the paper, and then the information is digitized. And then you have maps like this. This is a certain area in Kenya where we have real-time surveillance, near real-time surveillance of where malaria is and what the malaria prevalence is. And we also have ideas, and we're doing some projects where we can use the same scan form technology in agriculture. I can go into some more details on this. Just feel free to interrupt me if you like. I think I'll probably skip ahead of this, preaching to the choir here. Our motivation is really the smallholder farmers. We're very mission-oriented company. So in fact, some of us have even been living in villages trying to understand how the smallholder farmers are living. And I guess the figure I want to highlight here is that Sub-Saharan Africa has 20% of the world's arable land, but is only using about 2% of the world's fertilizer. And this fertilizer, of course, there are many different factors for how to improve crop yield, but this seems like one of the simplest things we ought to be doing in order to change some of these countries from net importers of food to net exporters like they once were. And here's an illustration I like to show of the yield gap, where we see in Kenya, for example, this red curve is showing the theoretical maximum, the number of say tons of maize per hectare that I can grow, and then the yellow is what I've actually achieved. So in places like Nebraska, we're maxing it out by using all conceivable technologies to reach the maximum. And then in many other parts of Africa, we're well, very, very far below the optimum. So we want to kind of close that gap. So yeah, these are some of the examples I had mentioned of our kinds of approaches, which we think we try to be quite practical about what we do. So I can go into more details about some of these if you like. I think I'll just jump to the cropland mapping. So here are some examples of the mapping work we do. So here in Nigeria, we're mapping all the croplands across the country. We did it in 2020. We're doing an update now in 2022, and soon we'll be able to show the differences between the years. And we try to achieve accuracy and precisions above 85%. And then over here, you can also see we're working hard on R&D to map exact field boundaries, which are very, very difficult to do here in Sub-Saharan Africa. We have such small plots, just a few acres, and sometimes they're not rectangular. Sometimes they can be shaped like slices of pizza, and all different kinds of shapes in different places. So maybe I'll just I'm gonna skip ahead like this. So these are examples of some of the old maps that people have been depending on. And also, if you ask the Food and Agriculture Organization, FAO, what's the percentage of cropland in Nigeria, or how many hectares of cropland there are in Nigeria, you'll see the same numbers from year to year, 34 million, 34 million, 34 million, right? And it's done by some kind of manual estimation and based on legacy data as well. So what we try to do is for every single pixel at 10-meter resolution, we're trying to map it to whether it's cropland or not. And we do this through a combination of machine learning plus, of course, training. Like machine learning is only as good as the examples and the training data it gets. So the training is done through an application we have called GeoSurvey, where people can look at satellite imagery and they try to mark if they think this is cropland or not. So by giving a small percentage of the country as examples to GeoSurvey, we can then train deep learning to try to map the rest of it. Of course, then training those people who are doing GeoSurvey also has to be done very carefully. And so here we have some pictures of me and David in Nigeria surveying the place, trying to understand, okay, what does this look like on the ground and how does it correspond to something in the satellite? So here's some examples, as I mentioned, automated plot boundary mapping. And so, these are all building blocks that are necessary in order to get to crop yield. We all want to do the yield estimation, I know, but before that, we have to see, can we do these basic things? Can we even count? Can we count what are the number of hectares of cropland out there? And then can we count boundaries? Can we count how much maize, cassava, sorghum, rice, differentiate these things? Can we see where people live and then try to optimize our intervention based on where they live? So let's do these basics first. So here's another example through the magic of AI, mapping, again, houses and croplands. Here's another example where we start mapping different kinds of land cover. So there's yellow as croplands, and we have dark blue as water, forests, and alluvial plains and things of that nature. So this was actually very useful for planning soil sampling expeditions. That was how our whole cropland mapping work started. We had teams of people going out there into the field wondering why is it that we go out into the field on a random sampling design, and sometimes we dig into the ground and we get rocks, right? You're wasting my time. It's hundreds of dollars every single time going out there. Can you just make sure that every time I go out there this time, I'm definitely going to dig into some soil that's crops, and this helps optimize those kinds of sampling expeditions. So very quickly, here's another example from Nepal, where we had a 5-year project with USAID to build a national seed and fertilizer system. So we just did a very small part of that together with CIMMYT. And we were working on this mapping. So first they wanted to know where are all the buildings, and so we can produce this sort of automated map of where people live. And then you can have a full geospatial strategy. So here I've shown all the croplands. And by the way, you need different models in different places, because as you can imagine, you have these stepped terraces in Nepal and a mountainous region, completely different from some other parts of the world. So all this orange I'm showing here are croplands. Then I've added highways and houses, and we've added some agro dealers here through people on motorcycles driving around. So thanks to this kind of information, now we can start thinking, if I wanted to add another agro dealer or another fertilizer shop, where should you put it? How far does this guy down here have to drive to get to the nearest drugstore, right? So this kind of information, which was deployed across the whole Feed the Future region in Nepal, was then integrated into National Agricultural Policy. So this is the National Soil Science Research Center's own, map, their own portal. They take the work that we did and we integrate it into that. So we would love to have more examples of this kind of adoption in other parts of the world as well, such as Africa. Okay. Here's another example where we can detect kinds of climate change. There's a certain map in 2020, another map at the same place in 2022. The computer can then rapidly identify that something has changed. The cropland has completely changed, and it shows up in this bright red, like a warning sign. And this is an example of flooding that happened in the region. Please interrupt me if I'm out of time. Please regulate me. So I want to say more about our work in rugged data collection, advancing market intelligence in Africa. And so we've been working very well for many years with our partner AFAP, the Africa Fertilizer Agribusiness Partnership. And as you know, AFAP has been financing many different hubs and hubs to distribute more fertilizer throughout many different countries. And so by using tablets and phones, collecting data all across these regions, we're able to produce maps like this where we can see and visualize the business relationships between hubs and retailers. So normally I would have an interactive presentation here, but I have a few slides where I can just simulate the interaction. So these are all different kinds of retailers, and for each one, we know what they're selling, We know which hub they're connected to. We also have some information with farmers that they're working with. So if I click on this node, I can see more about the name, the owner, and so on. And this sort of information can then lead to things like this, fertilizer cost buildup diagram for Ghana, where based on all the data, we can see why is it that when the fertilizer is in the plant, it costs this much per ton, and then after all of these steps, it later costs this much. So that could be a point of discussion. Did we really need to increase the cost this much all along the way in order to deliver these goods to the farmer? I'll show you another example. This is the plant telemedicine case. So some of you in the audience may be agronomists, and you could tell us what's wrong with each of these plants, but most people are not able to do that. Right? And in many organizations, the number of people who can do this is very few. So this was a project we had done with 1 Acre Fund that I mentioned already. Rather, those 4 people who are trying to manage 500,000 farms, they can just sit in an office now rather than running around, and they just play with this app all day, where they can say what's wrong with the plants, and that information can be sent back to the extension worker and then to the farmer. It's also a way of training people. So if I click on the question mark and say, I didn't have this training. I'm a computer scientist. Well, thankfully, the agronomist had carefully prepared all these examples. So you can look at the examples and learn how you might diagnose. And there's also a review system where you can audit and make sure that the diagnoses people give are correct. Did I hear someone?
2 minutes, William.
Okay. 2 minutes. Okay, thank you very much. So I think I'll move ahead a bit faster. So I'll say a little more about this paper project. I think it's very useful. I think paper is extremely underrated. This aligns with our idea of practical systems for practical ways of using technology in agricultural development. So this all came from the health space, and we really should. It's not paper that's the problem. It's rather digitizing the paper. If you can digitize the paper, it's great. So that's what we do. We allow you to continue writing on paper. Then you take a photo. Okay, and this is an example from a register about antenatal care, pregnant mothers. In 60 seconds, actually about 40 seconds nowadays, you get your digital data. So you can continue writing on paper. And so if anyone who has worked with extension workers in any of these countries, hopefully you'll get the point that this is actually very useful. If you start distributing tablets to extension workers everywhere, you're going to lose them. It's a huge expense. You can't even start the project. But this will allow you to start the project. This has also been used by the World Health Organization to help evaluate the recently approved malaria vaccine, using tens of thousands of people in the community. So these are some examples of people using ScanFarm in the community. And yeah, it's growing rapidly. We have now about 13 million patient records. So we're trying to apply this more to agriculture, and we're very happy to learn more about how you guys think you could work with us and AFAP on using this kind of technology to collect more data in the field. This is a project we did with CIMMYT, where they're using this to try different kinds of varieties of maize. And if you're doing a randomized control trial and you're out there in the hot sun staring at a screen that you can barely see, you're squinting at it, you have to come back to it, and you're navigating all these menus, it's really a pain. So paper is a good way to collect the data. In fact, when we did a survey across all of the people who are doing breeding trials on wheat that are connected to CIMMYT, the vast majority of them, I think like over 80%, all admitted, yeah, we actually write data on paper first. And then we manually transcribe it. So let's just skip that step and get the data back faster. So getting back to fertilizer, we really all want to know more about the smallholder farmers. And the smallholder farmer data is very important to improving smallholder agriculture. But so far, it's been very hard to collect that data. We use the wrong kind of technologies in the wrong places. And most agro-dealers just lack the technology to know your customer. So we're hoping that this kind of technology that I've been describing can be a way to finally get that last mile much more easily. You write on paper, you capture it with one click. And so this way, the fertilizer industry can have a way to connect all the way down to the last mile. Okay, and I know I'm out of time, so very quickly, there's some expensive ways to analyze plants and soils like this. And we're trying to make that much cheaper by reducing the cost to things that you can hold in your hand for just a few $100s. And if you're interested in more about that, feel free to contact me later. So I will just quickly conclude.
Thank you.
So my
William.
thoughts about technology? Yeah. So my thoughts about technology and ag development, please try to customize it for the realities on the ground. More expensive doesn't mean more effective. And we should try to merge plant, soil, and fertilizer science with engineering and computer science. Thank you very much.
Appreciated, Dr. William. Thank you very, very much. A round of applause for him.